pull the microphone down from my stream height.
Oh yeah, thanks. Yeah. That's good. Am I audible? Okay. So, hi everyone, thanks for coming. I'm Norbert from Gevulot. We are building a decentralized cloud for ZK. But first of all, I'd like to talk about how to decentralize proof generation from a conceptual perspective, like protocol design perspective. By the way, I'm doing protocol design at Gevulot and also involved in product. Okay, so basically, let's take a quick general outlook on like the past 1.5 years. In 2023, the major discussions, I remember a couple of them actually at EthCC last summer. Major discussions were around sequencer prover separation, also the prover decentralization of L2s, and like whether they should enshrine or not enshrine prover networks. That means, should they build their own in-house prover network to decentralize their proving activities, or should they go with a third-party prover, outsourced prover? Now, the third-party proving, obviously, it saves a whole lot of complexity because the go-to-market is much faster. But then, depending on who you choose, you may introduce some external dependencies. It may introduce, depending on the design considerations of the chosen provider, it may introduce some liveness or censorship risks, etc. On the other hand, if you go with in-protocol prover networks, it brings a lot of like kind of trade-offs. You don't have the external dependency, but then depending on when your prover is allocated a job, they are sitting in idle basically. So the hardware utilization is definitely not optimal there. And there, like in-protocol prover networks would have created a whole bunch of fragmentation, meaning that node operators would have operated a bunch of different nodes on different networks of the L2s had they built their prover networks in-house. Now, the reason why I'm talking in past tense is because in 2024, it became clear that basically the industry leans towards outsourced proof generation. Now that brings a couple of other challenges. One of them is for example, it brings about a new type of fragmentation actually, fragmentation of the prover infrastructure landscape, because currently like there is a big bucket, so-called prover networks or proof markets, and most of the providers are just thrown into the bucket, and it's kind of challenging to see who is focusing on what, even though there are actually pretty different focuses in the landscape, and it's challenging to find which is the most suitable solution for any project that is looking to outsource proof generation. Now there is one solution that is being getting started to be discussed, which is ZK Boost. It's been announced I think this week, but there have been talks and coordination around that for the past 2 months. I think the main goal of ZK Boost is to create a standardized API for proof outsourcing, where any proof provider can plug in from one side, but then any project with ZKP demand can plug in from the other side, and like any proving option would be made available through this standardized API. Anyway, that's just a side topic. It's good to see that abstracting away the complexities of proof outsourcing is being discussed about more and more. It's been lacking in the past months. Now, let's come back to decentralization, which is the main topic of my talk today. Why does it matter so much? From our perspective, since proving is a compute-heavy task, it's really susceptible to centralization, and we don't want to replicate the same thing what we've seen with traditional cloud compute. So centralization impacts other risks as well. So it's not an issue in itself, obviously. It may introduce liveness risks, it may introduce risks of one dominant entity starting to control cost structures, it may introduce censorship, etc., etc. So it's definitely, we need decentralization focused mechanism design principles to address these consciously when designing prover networks or like any proving solution that outsources proving. Now, I've listed a couple of design considerations related to decentralized prover networks. Let's just run through them, and on the next slide we are going to particularly talk about the workload allocation mechanism more, because that's a key element, I think. So participation is the first thing you want. Obviously, if you target decentralization, permissionless entry is very much is needed for that, like as a solid basis. But then, if you don't carefully match the workload allocation mechanism, then it actually can spoil whatever you have won with permissionless entry. It can spoil it on the other side. We'll talk about that in detail in the next slide. But for example, capacity verification, that's something that is, I think, a very interesting topic, because there are different approaches to what type of hardware to allow to join a prover network. Some teams are building prover networks allowing any type of hardware, from very specialized one to consumer grade, where it adds a whole lot of complexity to how do you want to distribute workloads. And very often the trade-off there is that you need to select an allocation mechanism that is more prone to centralization. We'll talk about that. Why? In case you have like you have, let's say, a clearly defined minimum hardware requirement, in that case you can obviously, with proper proof of capacity verification and proof of availability type of verification, you can make sure that you can, like the network can offer a standard top performance across all the active prover set. Now, reputation systems is something I like a lot, but I haven't seen an optimal solution yet that doesn't either favor new joiners or favor the old guys around the block, because it's super hard to define or to create a mechanism that is fair and inclusive. So, for example, what I've been thinking a lot about recently is whether kind of like a constant capacity and availability verification could serve as like, reputation may not be the best word in this sense, but like, let's use that, reputation on actual merits, on reputation on like continuous merits, something like that, which could be kind of neutral. As long as you have the capacity and you are available, you are considered reputable, meaning constantly being allocated jobs or something like that, but that's just a side note. Then we've got the question of economic security. Usually it's staking or in the recent months, restaking based. Yes, well, until a mass slashing even happens, restaking is a good option. And then if that may happen at any point, then teams may rethink strategies. It's no secret I'm a bit skeptical about restaking, but that's just my private note, not give a lot. I've been thinking a lot about whether there are alternatives to staking in that sense, because staking would serve the purpose to for provers to to act honestly and to have skin in the game. What if we consider a constant capacity and availability verification, meaning whenever they are not busy with jobs allocated to them and they have some idle time, we bombard them with mandatorily executable jobs that so that even in the idle times or in the time in between allocated jobs, we know constantly they are continuously available. And the reason why I'm thinking about this is because in case of a prover node, it's not like a validator where you spin up a pretty modest hardware, you can mount the validator and you need additional stake. in many cases, prover hardware costs tens of thousands of dollars anyway, and just to buy that, have that available, and keep that running is a pretty heavy cost element or skin in the game, so to say. So we've been thinking quite a lot about alternatives to actual staking, where with combined kind of proof of work to the like ZK mining. Just trying to make a quick parallelism here, but not the main topic of the talk. But these are things I've been thinking about in this topic. And then another thing is, can we positively incentivize honest behavior? So like, instead of saying, hey, if you act dishonestly, we'll slash you, instead of that, how could we build positive incentives to remain honest? I think that's always a much better motivation. And of course, in terms of economics and like in the general sense, absolutely, any prover node in any prover network, or any prover network out there working in a decentralized way, has to ensure in their economics that nobody can earn money. Like, they can only earn money acting honestly, and they definitely lose money if they act dishonestly. Whether it be future profits, whether it's slashing, there can be different approaches, but yeah, just as a generic principle. And then obviously fallback mechanisms. What if there is a prover failure? How do we handle that? Is that baked into the protocol? Or does an auction need to be restarted in case the prover who with the winning bid actually failed to generate the proof? So these are different considerations. Now, okay. Now a little bit specifically about workload allocation mechanisms. I think it's, as I mentioned, permissionless entry is really important to ensure and to allow proper decentralization, but the workload allocation mechanism is needed to maintain that decentralization long term, because some of the workload allocation mechanisms out there are actually heavily prone to centralization. One of these is auctions. They are always, or most of the time, they are looked at as the key mechanism to drive down costs. I think there are other ways. If planning proper economics and having the full flexibility to plan economics in a certain way, that could allow the protocol to provide cheap enough proving without the trade-offs that auctions come with. I'll talk about that a little bit later again, but like, what's my problem with auctions is that the richest entities could easily create monopoly by just underbidding everybody else. And there have been some really nice approaches. For example, Lagrange recently published a paper on double auctions. It's really nice. Hi, great to see you again. It's really nice. On the other hand, in the double auction, the bidder side, where the proof providers are submitting the bids in that case, the ranking of those proof providers is also mainly, like, the key factor is how much do they charge for proving. So even if you have sophisticatedly designed auctions, at the end of the day, the cost element for which prover nodes are willing to generate proofs is still a dominant fact, which still allows for monopoly. Now, and like, it's very easy to create monopoly in that environment. Not necessarily will it be created, but it's easy. And we've seen this type of like prover undercutting in some protocols already. Order book-based mechanisms are very similar in a sense that they can, like, creating a monopoly there is, again, quite easy. On the other hand, it's vice versa, because the richest entities can simply absorb demand at any price if they can afford losing money on proving or doing proving for like zero profit. And the reason why it's important, because as soon as there is an entity like, I don't know, one of the largest cloud providers out there who can afford doing proving with no profit for years. As soon as competition's out, they're like such entity could create dominance in these workload allocation mechanisms. Now, we could, in summary, we could call this like economic, like entities with economic wealth could create easily monopolies in auctions or book-based mechanisms. Now, for proof racing, that's a different story. It's kind of like proof of work. Everybody racing to do the job, but only the fastest gets rewarded. That's kind of like compute wealth type of monopoly or compute wealth-based monopoly. And obviously, it's never going to be the cheapest because of the redundant or wasted, depending on where we look at it, but the redundant or wasted computation included in proof racing itself. Now, the stake-based lotteries are somewhat more neutral. On the other hand, the richest entities still have the chance to be dominant because they just need to increase the amount of stake they have by the click of a button, and then they will have higher chances to be selected for a certain workload. So the most neutral allocation mechanism from the point of like with the lowest risk of centralization is pure randomness. And it's not the holy grail either, because you need to design other elements of the network in a way that randomness can properly show its strengths. For example, you need, if you want to go with randomness, you cannot just simply onboard any type of hardware, because one will be much more performant than the other, and you may be allocating to a hardware that cannot fulfill a job in the allocated amount of time. So you need other elements of the protocol there to be designed accordingly. But still, if we look at it and we're talking about how to decentralize proving, that's the most neutral and workload allocation mechanism that with which you can maintain actually your decentralized setup. Yes, in this slide, I touched already a little bit upon what is our approach, Gevulot's approach to decentralized proving. But let's look at it from the perspective of L2s. How would layer 2 solutions design their own prover network? Let's imagine we go back to 2023 and the industry doesn't want to go with outsourced proving. They would design their own networks and build them, like not just have the sequencer in-house, but a decentralized prover network in-house. Participation would obviously be permissionless if they want to maximize decentralization. The workload allocation would probably be randomness based, just like for the validators or for the sequencers, if they want to maintain decentralization. And we've seen this being used, in most of the L1s when it's about like neutrally selecting a certain actor in the network to do some job. Regarding economics, obviously, promoting honest behavior and punishing dishonest behavior would be key. And probably the L2s would have some built-in like fallback mechanisms baked into the protocol to make sure that, to ensure liveness of their protocol in case the randomly selected prover fails. Now, these are characteristics that we can all check with Gevulot. So we've been designing our ZK cloud to meet the expectations of L2s, meet the expectations that L2s would have of their own in-protocol prover networks. And I think it's really, but they just don't need to build it anymore because there is a solution out there. So it's I think it's very important from that point of view. So basically, now I'll talk a little bit about what we are building and how we approach decentralization, and hope this will be also useful and try to give it in a practical perspective or in a practical way. So our core principles, or our main thought process, is that we want to we build our protocol with decentralization focused design elements to ensure that no one can control where proving happens, to maximize liveness guarantees, to minimize censorship, to make it trustless, neutral, etc., etc. We know all these, but unfortunately, in the past, I don't know, in the past 1 or 2 years, maybe the importance has been forgotten a little bit. The importance of decentralization, and it's really great to see L2s, for example, that have been running in a centralized fashion for years, basically, many of them, opening up, building a path toward decentralization, even some of them already starting initiatives, contests, whatever, out there to actually decentralize their proving. At Gavulot, we believe in a ZK future where proving is truly fast, cheap, and decentralized. And these are the principles along which we've been building ZK Cloud as well. ZK Cloud is basically the first universal proving layer for ZK. It allows users to generate proofs for any proof system. We're going to talk about that a little bit, with dramatically lower costs. The architecture consists of 3 main elements, basically: proving layer, orchestration layer, and compute layer. The proving layer is universal in a sense that it can support any proof system. You can either use some of the pre-deployed provers on the network, or you can deploy your own, kind of like bring your own prover boundary and deploy it on Gavulot. Either way, this helps us to aggregate workloads from across the industry. Now, regarding the orchestration, we've got a blockchain-based mechanism, very minimal Cosmos-based chain underneath. Basically, we don't host smart contract state. We have very minimal operations, but it's just needed to manage workload distribution and reward distribution in a fair and balanced way. And also, we needed that because, as I mentioned to you, we needed the full flexibility in designing the economics in a way that we can make proving cheap enough, even without applying an auction, but going with randomness and focusing on decentralization as well. So we've got node and network level orchestration in ZK Cloud that increases also the overall hardware utilization on one side and decreases the cost of proving further. And we've got the execution guarantees, like fallback mechanisms. You can add additional redundancy to your proving job if you want, etc. And it's a decentralized compute layer. Underneath, it's permissionless. You can run GPU, CPU provers, or plug in custom hardware as well as they become available. I'm sorry, I can't see that. Pardon?
1 minute.
1 minute. Oh, I'm sorry. In that case, I'm talking too much. Sorry. Let me then jump here. Yes, introducing Firestarter. We've been facing some delays, but hopefully in the coming days, actually early next week, we are finally launching Firestarter. It's an end-to-end implementation of the ZK Cloud. We've got a decentralized infrastructure for proving behind, but we run the validator set in a permissioned fashion. That's the only difference. It's scalable, it supports any proof system. We've got some of the available provers listed there. ZK EVMs and ZK VMs, both. Provers run in containers on a Linux VM. That's a big improvement compared to our DevNet. And we go with a pay-as-you-go pricing model. So you don't waste any more money for idle time. You only pay for what you use. And it's very ideal for parallel builds, like, for example, RISC-0's segment proving or STEX proof tree construction. And like one last thing, 2 4090s in our GPU nodes, 64 cores and 400 gigs of RAM. That's what we get for 84 cents an hour if proving with us. If you extrapolate it to a monthly figure, that's probably a bit more expressive. It will cost like $600 per month for 2 4090s and the rest of the thing. That's the user cost. If you as a user want to do proving on Gavulot. Same thing for CPU nodes. 96 cores, 700 gigs of RAM. That's the minimum specs in our protocol. 61 cents per hour or $440 a month. That's what you will pay. Obviously, you only pay for what you use. So when you submit a proof request to Develot, you actually define how many CPU cores you want to be allocated to your job, how much RAM, how many GPUs, and the compute time within which you expect, with the allocated hardware resources, your job will be completed. And last but not least, if you want to run a prover node on our incentivized network, scan the QR code. Here are the more detailed specs for GPU and CPU node. You can bring your own hardware or you can rent a prover node as well. You get the same incentives in both cases. Yes, so I think that's it from my end. If you want to learn more, visit our website or visit our docs, and yeah, let me know if you'd like to try out that. We're happy to chat more.
Thank you very much, Norbert from Develop. Big round of applause, please. Okay, but this is the end of